Okay, today we're going to be talking about Cauchy sequences. This is when you can prove convergence, but you don't know the limit. You don't have a target value. And we're going to start off today with a definition of a Cauchy sequence. We say the sequence AN is Cauchy if for every epsilon greater than 0, there is an n such that if n and m are greater than capital N, then this implies that the difference between a sub n and a sub m is less than epsilon. Okay. Note that in this case, that a sub n is an element of a sub capital N minus epsilon, a sub plus a sub capital N plus epsilon, and in that little epsilon interval surrounding the a sub n for all little n that are bigger. So you get in closer to this point, to this a sub capital N, and you're in within that interval from that point on out. Okay. This will help us in one of the proofs that we that we have ahead of us. Okay, and so what we're doing now, we're going to prove that a sequence of real numbers converges if and only if it is Cauchy, and that this has two halves of it because it's an if and only if. It has the first half, which is an easy, and the second half, which is going to be a bit more confusing. We start assuming that we do have our honest to goodness convergent sequence, and that it converges to a particular value A, so some number A. Okay, so we're going to show that AN is Cauchy. So we let our epsilon greater than 0 be given, because what we're doing here, we're just checking the definition. We then need to find an n which satisfies the conditions in our definition. And so, you know, in a perfect world, the n we have here would be exactly the same here. But the world isn't perfect, so we're going to fudge a little bit. We choose our capital N, so so that AN is within epsilon of A, but so that AN is within epsilon over 2 of A. Okay. Now, given this n, we're just a bit farther along than we would for plain convergence. Suppose that n and m are bigger than this capital N. Okay, now let's look at the distance between AN and AM. Well, we have no idea how far apart they are, relatively speaking, but because it converges, we do know how far they are from A. So I put in a capital A, and I take out a capital A and I put it back. So I am adding a 0 right in here. Okay. And then I trade my equal for a less than or equal because of the triangle inequality. And now, okay, I know that AN minus A is less than epsilon over 2 because little n is big enough. I know that A minus AM is less than epsilon over 2 because little m is big enough. So together, epsilon over 2 plus epsilon over 2 adds to epsilon. And so I know that AN minus AM, excuse me, I know that it's less than epsilon. So, okay, I'm just all over the place. Okay, right there. All right, this is it. So therefore, AN is Cauchy. Now we need to go the other direction, which we're going to assume we have a Cauchy sequence and then show that it converges. But the only tool we have for showing convergence is convergence to a target value. So we're going to have to come up with a target value. We need to construct a number to which my AN converges. And to do this, I'm going to apply the nested interval principle, because this is just about the only technique we have now to prove that a real number exists. Okay. So let n sub 1 be chosen so that if n and m are beyond n1, then they have to be within 1/2 of each other. Okay. And now I'm going to construct a closed interval I sub 1 to be a closed interval that's centered around A sub n1. And I'm going to do it, have the radius, as it were, of this interval be 1 instead of 1/2. This is because I'm a bit conservative. I want to make sure that my intervals stay nested. Okay, so if n is greater than n1, then A sub n is contained in an1 minus epsilon an1 plus epsilon, which is contained in the closed interval I1. Now I'm going to choose an n2. I'm going to make sure my n2 is bigger than my n1, and then if I still need to, I'm going to choose it so that if n and m are bigger than n2, then they're within 1/4 of each other. And so I'm going to let my I sub 2 be an interval, closed interval that is centered on the A sub n sub 2. And again, of course, my A sub n's are going to be contained in my I sub 2. And I continue this way each time, constructing an interval so that I sub k is half as long as the preceding interval, and that if A sub n and that A sub n is in I sub k if n is bigger than n sub k. Okay, so here we hit it with the nested interval principle. There is a unique A that is common to all of my I sub k, and we claim that A sub n converges to this A sub k. All right, well, showing convergence isn't too hard. Let epsilon greater than 0 be given. Choose k so that the length of k, I sub k, is less than epsilon. Now suppose n is bigger than n sub k. So then A sub n is in I sub k, which then must be contained in A minus epsilon, A plus epsilon. Therefore, A sub n minus A is less than epsilon. And it follows from definition that A sub n converges to A sub k. So all of our difficulty here was rolled up in in getting our target value, using the nested interval principle to get the target value. Okay, so we have a corollary to this that says, and it doesn't seem like much, but it turns out to be useful. It says that if A is equal to A1 plus A2 plus A3, if this infinite series converges, then the sequence of terms converges to 0. So suppose that A equals A1 plus A2 plus A3, so suppose that converges, then its sequence of partial sums converges, and furthermore is a Cauchy sequence. Okay, now we wish to show that AN converges to 0, okay? Well, let epsilon greater than 0 be given. And there is then an n, so that if m and n is bigger than n, then an minus am is less than epsilon. Suppose that n is then equal to capital N plus 1. Okay, so I do that so that I can get n and m, n and n minus 1 both bigger than a sub n. So a sub n is equal to capital A sub n minus a sub n minus 1, and that is less than epsilon. Therefore, my sequence converges to 0. Now, this does turn out to be quite a useful thing, okay? And I'm going to stop sharing my screen now, and I'm going to share a different camera. Hold on. I'm going to switch over to my document camera. Okay. Now I have my document camera is going to do some writing here. And so this comes down to viewing this. We have, let's see, if the sum A equal A1 plus A2 plus A3 converges, then, okay, AN converges to 0. Okay. It's in the form if P, then Q. And in symbolic terms, this is P implies Q. Okay. So P is this part, and Q is this part. Okay, now P implies Q is mathematically equivalent to its contrapositive, or logically equivalent to its contrapositive, which is not Q implies not P. Okay. And so this is if AN does not converge to 0, then A equal to A1 plus A2 plus A3, etc. does not converge. Okay, so this gives us a test for showing that a series does not converge. I can now look at, say, have a series S be the sum of n equal 1 to infinity of -1 to the nth power, okay, which is 1 minus 1 plus 1 minus 1 plus 1, etc. Which, I mean, I can do arguments here to show that S is equal to 0. I can do arguments to show that S is equal to 1. This is, hey, your sequence -1 to the nth power doesn't converge. In fact, it doesn't converge to 0, so S doesn't converge. Now, so it's useful in situations like this. Now, where it can be confusing, and if you go ahead and teach calculus someday, you're going to spend some time showing that the sum of n equals 1 to infinity of 1 over 1n to show that this diverges. I mean, we've already spent a considerable amount of time in the course showing that this diverges. And your students are going to nod their head and say, oh yeah, interesting. Then you're going to state this theorem that we just said, and they're going to say, well, since, okay, the limit as n goes to infinity of 1 over n equals 0, then the series n equals 1 to infinity of 1 over n converges. And okay, that's not what the theorem says. It says if this doesn't go to 0, then this diverges. Okay, this is because the contrapositive is more difficult than it is generally believed, and so you have to be careful when you teach this, because your students will get it wrong. Okay, let's see. Now I'm gonna stop recording this. Now.